Hello everyone, welcome to the Math 262 Coronavirus Edition. I know that you are all probably at home right now, and I wanted to try a new format for class. I know that class does not officially begin until Thursday, however, calculus is a very important class that I think is best learned in pieces. So I'll be posting a video each day that we would normally have class, and then you will watch the video, pausing it at the appropriate times, and take notes and work problems. I'm in the midst of figuring out how exactly we're going to do office hours. However, in the meantime, I'm probably going to create a forum online that we can ask questions and answer each other's questions. Anyway, well, it's best to get started and see what we can do. Feel free to pause the video at any time. However, my expectation is that you take notes during the video and then you will upload them, and that will be my way of knowing that you are keeping up with these videos. There'll be an assignment you can post your notes each day. Quick reminder, we're still going to have WebSign due Friday, half of the material you learned before spring break, and the other half we're going to learn momentarily. I think that's about it. So let's get started. So we've learned a series of tests already. We've learned about the divergence tests, the geometric series, the p-test, the integral test, and we're going to try another example. So let's look at an example right here of a sum from n equals 1 to infinity of 1 over n squared plus n plus 4. Now, you can do this series and show whether it converges or diverges by the integral test, but nobody's got time to do that today. We want to know if there's an easier way. So observe the following. Observe that this fraction is always less than this other fraction right here. You see that the n squared is smaller than the n squared plus n plus 4. Therefore, when you put them in the denominator, you see that 1 over n squared plus n plus 4 is less than 1 over n squared. So what do you think happens? Well, what happens is that it's not so hard to see that this sum must be less than this sum on the right. And we know that this sum on the right converges by a p-test with p equal to 2. And we know that the p-series will converge for p bigger than 1, and it will diverge for p less than 1 or equal to 1. And we see that here we have the sum of the series 1 over n squared, and the p is 2 in that case. So what this tells us is that this sum must converge. Because it's positive and it's less than another sum that we know converges. So what does the converging mean for the sum on the right? For the sum on the right, which I will highlight here, this sum we know converges to a finite number, a positive finite number. Therefore, the sum on the left must converge to a smaller positive number. So this is in essence what we call the direct comparison test, and I'll write that now. So what the direct comparison test is, well, we don't want that color. The direct comparison test tells us the following. It tells us that if we have the following terms of our sequence, the a_n and the b_n are the terms of the sequence. They aren't the sums, they're just the actual terms. And if we know this is true, then the following will hold. If we know that the sum of the b sub n's converges, then we know that the sum of the a sub n's will also converge. Conversely, we also know that if the sum of the a sub n's diverges, then this will tell us that the sum of the b sub n diverges as well. So basically what this is saying is that, let's look at case 1 right here. What this is saying is that if we know that we have these terms b sub n, and if we add all of them up, and it is a finite number, less than infinity, and we also know that the a sub n's are smaller than the b sub n's, if we add up the a sub n's, it must also add up to a finite number because the b sub n's added up to a finite number. Conversely, let's consider case 2. In case 2, we say that the sum of the a sub n terms diverges. This means that if we add them all up, it adds up to infinity. Since the a sub n's are smaller than the b sub n's, if we add up the b sub n's in the second sum, it must also add up to infinity. So now that we see that we have the direct comparison test, I want us to do 2 examples, and after I write them, I want you to pause them and see if you can figure out what are the terms that you want to compare it to. In essence, the direct comparison test is a test we use when the sequence we have, or the series we have, is very similar to another series that we can easily tell if it converges or diverges. So let's take a look at 2 such examples. In the first example, we have the sum from n equals 2 to infinity of 1 over the square root of n minus 1. And in the second example, we have the sum from n equals 0 to infinity of 4 to the n over 5 to the n plus 2. I want you to pause the video now and try to determine what should we compare these series to. What other series do we know that we can easily determine whether they converge or diverge using another test, and then compare them to the ones we have here. So pause the video and see if you can figure that out. Okay, now that you've had some time to think about it, let's look at the first series. If we look at the first series, we see that this -1 term in the denominator is a bit distracting. So we want to compare it to a series where that's not a part of it. 1 over root n. Now, we see that this series on the right can be written in a slightly different way that you might find a little bit easier to discuss. We see that it's actually a p-series with p equal to 1/2, which tells us that it diverges. So we know that the series on the right diverges. Well, how does it compare to the series on the left? Well, we know that 1 over root n minus 1 is always bigger than 1 over root n. We know that because root n minus 1 is smaller than root n. Therefore, the fraction 1 over root n minus 1 must be bigger than the fraction 1 over n, root n. And this is clearly always bigger than or equal to 0. So what this tells us is that the series n equals 2 to infinity 1 over root n minus 1 diverges by the direct comparison test. Okay, now let's turn our attention to the second series. What did you compare it to in this? Well, you probably compared it to the series where we just have 4 to the n over 5 to the n, which is the same as the series 4 divided by 5 to the n. This is a geometric series with ratio 4/5. That's less than 1. So what it means is that this series converges. Well, how do the terms of this geometric series compare to the sum or the terms of our first series? Well, it's pretty clear to see that the terms of this first series are always less than the terms of our second series here, because the terms in this series have a bigger denominator than the terms in this series on the right. So 4 to the n over 5n plus 2, those terms are smaller than 4 to the n over 5 to the n. And therefore, what this should tell us is that the sum from n equals 0 to infinity of 4 to the n over 5 to the n plus 2 converges by direct comparison test. Sorry for the messiness here. So that's wonderful. We know that if we have a series that maybe we can't calculate the, whether it converges or diverges, we can at least maybe compare it to another series that we know about. And so in these two cases, we found what they were. All right, so we've looked at the direct comparison test. However, what if we need to look at a series that looks a bit like the following? Three to the n over 2 to the n plus 5. Now, in this series, we say, okay, I want to compare it to the following geometric series. Now, I know that the series on the right must diverge because this is a geometric series with ratio 3/2. However, let's compare the two series, the terms of the two series. If we look at the terms, we see that the terms on the left are smaller than the terms on the right. That doesn't help us. We know that the sum on the right diverges, but we know the sum on the left must be smaller than it. The direct comparison test does not help us in this situation. So what can we do? Well, let's look at a limit to see what happens. So if I have a limit here, where I look at the limit as n goes to infinity of the terms of my first series, that was 3 to the n over 2 to the n plus 5, over the terms of my second series. Let's calculate this limit. Well, we see that the 3 of the n's cancel out, and we get the following limit. We have 2 to the n over 2 to the n plus 5. And let's multiply the numerator and the denominator by 2 to the minus n to obtain the limit as n goes to infinity of 1 over 1 plus 5 over 2 to the n. If I take this limit, I see that the term in the bottom, right here, must go to 0, because the denominator of that 5 over 2 to the n term is going to 0, or going to infinity, and so the fraction is going to 0. So this limit must be equal to 1. So what is this telling us? It's telling us that the terms from my first series, right here, are roughly 1 times the terms of this second series right here when n gets big. What this is telling us is that the convergence or divergence of the series on the right in green must be linked to the convergence or divergence of the series on the left. And so what this is telling us is what we call the limit comparison test, which is stronger than the direct comparison test, but requires a little bit more work. So the limit comparison test tells us the following. It says if the terms of both my sequences are always positive and their limit of their ratio equals a positive number, equals L, where L is finite and positive, L is 0 does not count, L is finite and L is bigger than 0, then this tells us that these two series either must both converge or both diverge. It cannot be that one converges and one diverges. That's not allowed. So the limit comparison test is a way of showing that if I know one series converges, I can use it to show this other series might converge. And similarly, if one series diverges, we can show that the other one diverges as well. And so in that previous example, let's bring it up here again. I've written the previous example again. We have this series on the left, 3 to the n over 2 to the n plus 5, and the series on the right, 3 to the n over 2 to the n. We know the series on the right diverges. We know that the a sub n's are always positive, and we know that the b sub n's are always positive. And furthermore, we just showed above that the limit of the a sub n's over the b sub n is 1. That is a positive number that is finite. So what we conclude is that the first series that we wrote down, the sum of the 3 to the n over 2 to the n plus 5, diverges by the limit comparison test. Okay. So you see that with this limit comparison test, it gives us a better way of taking our original series, getting a new series, and we know that this new series converges or diverges, and using the limit comparison test, we can assess whether our original series converged or diverged. So I'm going to write down 2 examples, and then I'm going to let you think about what are the series. Well, I'll do one example and then we'll do another example. And I'm going to write down, like, what do you think the series is we need to compare this to in order to use the limit comparison test? Okay, let's get started. Okay, let's write down the series. The series is the sum from n equals 1 to infinity of 2 over the square root of n cubed plus 1. I want you to write down a series that you think we should compare it to. When you compare it to a series, you're trying to compare it to one that's pretty similar, but you get rid of a lot of the extraneous stuff, like maybe the constant on top. And you want to hit at the root of what's really driving the convergence or divergence of this series. So, pause the video and think about for a second what series you might compare it to. Alright, now that you've had time to do that, let's write down a new series. The series we're going to compare it to is 1 over the square root of n cubed, also known as the sum from 1 to infinity of 1 over n to the 3 halves. We know that this is a p-series, so it converges because p is bigger than 1. Okay. So now we need to take a limit. So we'll call the terms of the first series an and the terms of the second series bn. So if we take the limit as n goes to infinity of the an's divided by the bn's, we have 2 over the square root of n cubed plus 1 over 1 over the square root of n cubed. And if we kind of move some things around, this becomes the limit as n goes to infinity of 2 times the square root of n cubed over the square root of n cubed plus 1. Now you might be thinking, how do I compute such an integral? Well, if I multiply the numerator and the denominator by the square root of n to the minus 3, excuse my bad handwriting, I get a new limit. It's important to keep writing these limit signs until you're done evaluating them. So whenever I have two square roots multiplied by each other, I can multiply what goes on the inside, and I should get the following. I see that this piece on the right here must go to 0 because it's a fraction, and the denominator is being huge, so that little fraction circled in yellow must be going to 0, and therefore this limit must be 2. 2 is positive and finite. So therefore we know that our series must converge by the limit comparison test. That's great. So what we see happening here is, how did we get our series on the right? Well, essentially, we just dropped everything that wasn't the biggest term. And you're going to see this play out with another example very soon. So what you're going to become familiar with these limit comparison tests is what in the numerator and denominator is the most important piece. Okay, so let's do another example. So let's do the example. Another example with a more complicated looking expression. At first you're going to not be very excited about this, but I promise that it will become easy pretty quickly to identify what rules govern how we choose the series we compare to with the limit comparison test. So after you get done writing this series, I want you to pause the video and try to identify what series should we use to compare to it with the limit comparison test. Okay. Now that you've had a chance to pause the video, what do we do? Well, when you're trying to figure out what to compare it to, you need to know what is the biggest function in the numerator and what's the biggest function in the numerator. The biggest thing in the numerator is this n squared piece. And the biggest piece of the denominator is this n to the fifth piece. We know that n to the fifth is always much bigger than n or 1. So what that means is we should pick the following series to compare to. We should compare it to n squared over n to the fifth. And we know that that should simplify to just 1 over n to the third. And we know that this series on the right converges because it's a p-test, or it's a p-series, with p equal to 3, which is bigger than 1. So now, if the first sequence we have our a-n's, and our second series has b-n's, we need to take a limit as n goes to infinity of a-n over b-n. And at first, this limit looks a little bit atrocious. But you can probably see where this is going to go. Well, you do some algebra, and it takes a little while, but you eventually get it to something that looks like this. And what do you see now? You see now that this piece on the right is a rational function. That means it is a polynomial divided by a polynomial. The degree of the numerator is 5. The degree of the denominator is 5. And therefore, the limit is just equal to the ratio of the leading terms because the degrees are equal. You can also see this using L'Hopital's rule, which we won't worry about today. But we see that that number is positive and it is finite. So what this tells us then is our first series must also converge by the limit comparison test. So what we have seen today is we've taken these two tests. One's the limit comparison test and one's the direct comparison test. And what they take is they take a series that you don't know whether it converges or diverges. You kind of simplify it to another series that you can tell very easily it converges or diverges. Maybe it's a geometric series or maybe it's a p-series. And then you use the comparison test to take the convergence or divergence of the series that you know about to imply the convergence or divergence of this new series. That's all I've got for day 1. On day 2, we'll have a lot of examples to work out. I'll work out some of them, and I'll leave some of them for you to do because it's important to practice them. And we'll have the forum open in case you want to discuss them. Let me know if you have any questions. We'll do the best that we can. And I hope to see you all back at least soon. Take care. Bye.